This is problem 4-76. It's on page 203. Let's change the problem number. A mass of 15 kilograms of air in a piston cylinder device is heated from 25 to 77 degrees Celsius by passing current through a resistance heater inside the cylinder. The pressure inside the cylinder is held constant at 300 kilopascals during the process, and a heat loss of 60 kilojoules occurs. Determine the electrical energy supplied in kilowatt hours. Okay, so here's the system initially, and I think I know what's going to happen here. I think the piston's going to move up doing boundary work. Does that make sense? So if we go from state 1 to state 2, yeah, we may have electricity coming in here, and basically it's that electrical power that makes all this happen. But to do a quick qualitative energy balance, the electrical power that comes in here, the electrical energy that comes into the air, has to supply the heat loss, has to supply the increase in the temperature of the air, and the boundary work that's done, right? So basically all I've said is an energy balance, and I said that the, well, let's write the whole thing out. I'm going to take the system to be the air, and we know that the heat flow in less heat flow out plus work flow in less work flow out equals, in this case, the change in the internal energy of the air, right? That's all that we really have going on here. Okay, there's no increase in potential energy or anything like this because this is a closed system. Now, is there any heat transfer in? No, you could argue that there's heat transfer in because the electrical work comes in and generates thermal energy, or is converted to thermal energy, but I've included the coil inside the system, so there's no heat flow in. There is work flow in and there's work flow out, as well as heat loss. And the energy of the system changes. How do I know? I know it because the temperature of the air changes. Okay. So let's see what we can do here. We've got minus Q out, and were we told anything about that? Yeah, 60 kilojoules. So we know the magnitude of that term. The work flow in, the only form in which work flows into the system is electrical, and so that's what we're looking for. We do know that boundary work flows out, so I'll say minus WB. Notice we don't have the sign convention we had in 220. We just automatically put the things in the right place. If it flows in, they're positive. If it flows out, they're negative. Okay, you just have to know which way they're going. Okay, so anyway, that's equal to, let's expand this term a little bit. If we knew the mass in the system and the heat capacity, would we use CV or CP?
CV is air.
CV, not because it's air, but because this is related to delta U. Okay, that's one bridge I'm trying to build in your mind. So again, write that CP goes with delta H, CV goes with delta U. Okay, so this would be CV delta T. And I want to get to that point, right, because I need to get to that point because I know the temperature change. In fact, they told us the temperature in state 1 was, let's see, let's write it down, 25, and the temperature in state 2 is 77 Celsius. Okay, we know that the pressure is constant, so I'll just write it down, 300 kilopascals. And what else do we know? We know the mass is 15 kilograms of air, and that won't change. All right? Okay. So let's see, what do we have in the equation? M delta T, CV we could look up, that's not that big of a deal, right? In fact, CV for air, you'll eventually have this memorized, I'll just write it down for you. CV is 0.718 kilojoules per kilogram per Kelvin. You can go back to the appendix and look it up if you want. Pretty sure that's right. But notice we've got a problem here. We've got one equation and two unknowns. I'm going to show you two ways to solve this. At least I think I am. I'm thinking, right? We could evaluate the boundary work, right? Because think about it, the boundary work occurs at constant pressure. So go back to page 195 and see if there's a boundary work equation that would allow us to evaluate the the change, the amount, the flow, the boundary work flow. Page 195, which one of the boundary work equations could I use here? I don't want to use the integral one.
Isobaric.
Isobaric, that's right, because it's a constant pressure. So it goes like this, P delta V, right? V2 less V1. What P? Well, just the pressure. It doesn't matter if you talk about state 1 or state 2, the pressure is the same. So we need the volume. Could we get the volume of the air? Sure, we could use the ideal gas law. So PV equals MRT. If we rearrange this, the volume is just MRT over P. Okay? Now, of course, we could get fancy here and make a bunch of substitutions. This is 320. Why not? Let's do it. V2 would be evaluated as MRT2 over P2. V1 would be MRT1 over V1. Let's try P1. Okay, so all I've done is substitute for the volumes. That should be okay. Notice M and R are constants, and P2 and P1 are the same as P, so they just cross off. So let me pull out MR, T2 less T1. That's the boundary work. Okay. Now this makes it easy. All I have to do is plug in the temperature once. So 15 kilograms. The gas constant for air. You know what? Maybe 0.718 is the gas. No, it's 0.287. The gas constant for air is 0.287 kilojoules per kilogram per Kelvin. And you can look that one up later if you want. I think I got that right. T2 is 77. T1 is 25. The difference is degrees Celsius. Can I cancel this degrees Celsius with that Kelvin? Is that okay?
Oh, wait, no, it's a change, so yes.
It's a change, so yes, I can do that. The unit size of the Kelvin is the same as the unit size of a degree Celsius, so they can cancel. Okay, because that's all I'm interested in is the unit size here. The kilograms go away, so please break out your calculators, and let's see how many kilojoules of boundary work this represents. By the way, did I tell you guys you can get a HP48G or a TI calculator app for your smartphone? You have a graphing calculator on your smartphone. Pretty awesome.
So it'd be 222.86.
222.86?
223.
223.26. Okay. Anyone second that?
Yeah.
Okay. So there's the boundary work flow. Well, that makes our lives easy. Now that we've got the boundary work flow, we can rearrange and solve for the electrical work required, or the electrical energy required. That would be mCV delta T plus the boundary work we've calculated plus Q out. Okay, so the mass in the system again, 15 kilograms. Yes. Heat capacity at constant volume, 0.718 kilojoules per kilogram per Kelvin. Delta T, we can do that in our heads, right? That's 52. 52 degrees Celsius. Yeah, that's right. So we've got this first bit, plus the boundary work, which we calculated, here it is, 223.86 kilojoules. Sorry, I'm out of space, so I've got to break the line and add Q out, which we were told was 60 kilojoules. Okay. Now let's see if everything cancels nicely. Degrees Celsius and Kelvin again go away. Yeah, so we've got kilojoules, kilojoules, and kilojoules. So add all this together and let's see how much electrical work is required. Let's see.
844, or it's 843.9, so 844 is good.
Okay, is that what we were supposed to find? Determine the electrical energy supplied in kilowatt hours. Okay, so we've got to convert this to kilowatt hours. Now, there's a couple of ways to do this. We could do it from units, or we could just go to the back of the book and look for a conversion factor. Let's do that because it'll be easier. Okay, so kilowatt hour to a kilojoule. Here it is. The conversion factor is 3,600. Do you guys see it? It's on the left in the metric section, back of your book. The metric column, 1 kilowatt hour is 3,600 kilojoules. So let's see, 1 kilowatt hour is 3,600 kilojoules. So the kilojoules will go away. So just divide your number by 3,600. What do we have? 0.2344 kilowatt hours.
Yes.
Stay on the video. Is that what they had? Hey, we did it. What do you know? Worked out. They had 0.235. Why they rounded to that, we got something different, I don't know, but we did it right. Now, I want to continue with this example because there's something else we can do here. There's a trick that your author likes to use, and you might think it's the main point of things, and it really isn't. Okay, notice we were able to solve this problem by using a boundary work equation. Sometimes your author will do the following, and it might confuse you. Sometimes what he'll do is he'll say, well, wait a second, let's see. Let me do it this way. We want to solve for the electrical work, so the electrical work is MCV delta T. In fact, let me go back to delta U, because that'll make more sense. So delta U instead of MCV delta T. Let's see, plus boundary work plus Q out. And then you'll say, well, wait a second. The boundary work is P delta V. And the only time this is true is when the boundary work is for a constant pressure process, which is what we happen to have in this situation, right? And then you'll say, okay, well, delta U is just U2 less U1 plus P V2 less V1 plus Q out. And then you'll recognize that, well, U2 plus P2 V2, because I can put whatever subscript I want on the pressure, it's the same in both states, less quantity U1 that's coming from here, let me make it look more like a U and not a V. U1, notice there's a minus sign on V1, so plus P1 V1 plus Q out is still the same thing, it's just math. But this is the definition of enthalpy. And so instead of using, so now this is a delta H, right? So instead of using CV delta T, he'll do something like this, MCP delta T. Notice this is really exactly what we did because we had a delta T for the boundary work. And if you notice, one of the terms had, let's see, let's go back and look at it. One had MCV delta T. The other term for boundary work that we had, let me get rid of this because I need just a little bit. Actually, you know what, let me move this out of the way real quick. Remember what we ended up with for boundary work? We said the boundary work is MR delta T. Okay? If we were to add the boundary work, which is this term, to the internal energy term, what we would get is something like this. We'd have equals MCV delta T plus this we decided could be MR delta T. Okay, so this is M delta T multiplied by CV plus R. What is CV plus R? You remember?
Oh, it's
It's CP,
CP, yes, the other one.
right? And so you end up at the exact same place. Now I've stopped writing the Q out, but you see how that would continue through the equation. This is sort of a distraction. It's not really something that would happen all that much most of the time for a lot of the problems we work. Okay? So you can go either way. I prefer evaluating the boundary work separately because I like to see how big it is. I don't like putting them together because then the boundary work gets shoved in with the change in internal energy. Basically what we're saying is that you can add together, I erase the figure, you can add together the effect of the boundary work flow out of the system with the change in the temperature in the system. So it's like you can evaluate two things together where one is the amount the bank account changes and the other is one of the withdrawals. Okay, and I'm not crazy about putting those two together, but you'll see him do it quite a bit, especially if you look through the example problems in the book. I do recommend you read the example problems. I purposely work other problems from the back of the chapter so that you've got the example problems to look through and kind of get a different perspective, maybe a different thought process. Questions, comments?